So by flexibility method, let us take up this analysis of beams. As per the syllabus, the analysis of beams by flexibility method. So you have to select beams which doesn't have more than 3 degrees of static indeterminacy. Maximum type of problem which you can get, or only very few, about a dozen of problems only you will get for working purpose. One is this two-span beam, for which degree of redundancy is 1. This type of problem you will get. Another 2 spans or 3 spans you may get this. Here degree of redundancy is 2. Maximum another 1 more span beam, which are all simply supported at the ends. You may get, that's all. So this is another type of problem you may get. This is degree of redundancy 3. Suppose if it is fixed beam, here 1 degree of redundancy is this propped cantilever. This is 1 degree of redundancy. Then fixed beam 2 degree of redundancy. There are also indeterminate structures. Then you may get another type of problem. This is also degree of redundancy 2, and this type of problem. This is degree of redundancy 3. So maximum variety of problems you may get in the continuous beam analysis. Otherwise, the degree of redundancy will be more. You can expect only this type of beam problems. And loading always generally either concentrated load or UDL, or it may be eccentric concentrated load or triangular type of load or moment. Triangular and type of load and moment, they rarely come into picture. Only the 3 types of regular loading conditions you may get. That's why I listed the ready-made formula for the deflection at the ends. By selecting moments at the ends as the redundant, you can easily work out the problem in just 15 to 20 minutes. So let us work some problem on these continuous beams. Next we will take up frames. So now we will take up this beam. So let us take a 3-span simply supported continuous beam like this. This span 4 meters, this 6 meters, 3 meters, A, B, C, D. Here you can take a central concentrated load of 60 kilonewtons at center. Then you can take a UDL of say 60 50 kilonewton per meter. Then here you can have eccentric concentrated load of 90 kilonewtons and 1 meter from the right end. So you can take EI to be constant. Let us take up this particular problem for analysis today. So as usual, you can follow these 4 steps, whatever I have already given in the previous class. The first step, you have to find degree of static indeterminacy. Here, degree of static indeterminacy is 2. So as I told you, in all these continuous beam problem, unless the secondary load, settlement of support is given, so if you can work the other problem other than this settlement of support problems by taking moments as the redundant. That is the easier way. If support settlement is given, then you have to take one of the vertical reaction of support as the redundant. So otherwise, in all other type of problem, you select only the moments at the ends of the beam as each member as the redundant. So here, since the degree of static indeterminacy is 2, you make the structure determinate by selecting, as usual, by select support moments at B and C, that is M, B and MC as redundant or release forces redundant. So that means the basic determinate structure will look like this. You have selected the support moment here, that means you have to introduce an internal hinge at that point at B, and then at C also you have to introduce an internal hinge like this. Then here of course you can retain as it is, that is hinge support. So this is the basic determinate structure, and the direction of the redundant force or the coordinates of the redundant force. In this particular case, you can select by arrows in this fashion. Always the sagging type of movement, which is always positive like this. So on left side you can take clockwise, on right side anti-clockwise. It is sagging type of movement in each span. This you take it as the coordinate direction. Here this is one coordinate, that is second coordinate corresponding to MB and MC. This is the basic determinate structure, and this is MB, this is MC. Now the structure is determinate. And here, now you can just write the redundant matrices, what you have selected, that is R. R is nothing but MB, MC. You can generate this matrix R, and also you can generate the displacement corresponding to these redundant coordinates, which are nothing but DL minus DR, DR minus DL. That is support settlement, if at all it is given, that is DR, and DL is the displacement which occurs on account of these loads along these redundants. Along these redundants, we limit the release, so it is free to undergo displacement. That displacement we call it as DL. This is the matrix which we have to determine by calculation, and this also we have to determine. These are the two unknowns which we have to determine in the next second step. Second step, to find DL. So in this case, you can say DR, that support settlement, it is 0, 0, because it is not there, nothing is given. If the support settlement, if at all it would have been given, then don't select the moments as the redundant. You have to select the unknown reaction at the support where the settlement has occurred. That's very important property which you have to remember. That is your basic first step. Second step, this DS, that is displacements here, that is rotations along coordinates 1 and 2 on account of the loading given. You have to work out. That's second step. So first, we will take up the loading given. So that is the basic determinate structure. Like this, we have selected basic equilibrium structure in this fashion. This is the so loading. Here we have one load. Because of this load is arbitrate is 80 kilonewtons instead of 60 or 60, it doesn't matter. We take 80 so that calculations becomes easier. So because of this, it will deflect in this fashion. We have to find out this displacement which is corresponding to this coordinate 1, and here we have UDL. Because of this, it will deflect like this, and this displacement also when you find out. This is D1, this is also D1 corresponding to this coordinate 1 and corresponding to coordinate 2, that is this is D2 and this is also D2. So we have to evaluate this D1, D2, D2, and we have to evaluate that DL because of that. So this you can easily work out from your usual conjugative method or area moment method, because now the moment you introduce, release this moment, each of these spans becomes simply supported beings independently. You can just apply either conjugative method or area moment method or calculate the slope at the end. Or you can remember the formula if the loading is not all that complicated, and you can just evaluate that particular slopes. So therefore, this D1 or D1L along the coordinate L1, whatever the displacement due to the load, that will work out D1L. For this particular load, as I already told, if at all there is a concentrated load given here W, so this due to this particular load, its span is L, natural rigidity EI, the slope at these ends will be equal to WL squared by 16 EI. Similarly, if there is a UDL of intensity W kilonewton per meter length and then natural rigidity EI, the slopes at the ends is given by WL cubed by 24 EI. Here also WL cubed by 24 EI. So mind that here it is clockwise, this side it is anti-clockwise. I have already selected the coordinate direction on that side, clockwise. On the right side it becomes anti-clockwise, so that here I need not attach minus or plus sign for those deflections. Straight away I can retain positive sign only. That's why I selected, I told you in the beginning to select the coordinate direction in this static fashion at the end, so that you need not have to bother about any sign convention regarding the value of the deflection. Similarly, another loading case I have, that is an eccentric load W. If it is acting at a distance A from left hand, B from right hand, span L, natural rigidity EI, then this slope at the left hand, it is given by WAB by 6 EI into L plus B. Here it becomes WAB by 6 EIL into L plus A. So these three formula, if you remember, for standard loading cases, you can straight away write the external load deflection style. So D1L along with coordinate 1, here it is concentrated load. According to that first formula, it is W L squared by 16 EI. W is 80, L is 4 meters, that is 4 square divided by 16 EI. EI is EI itself constant, that is 16 EI. So next class, this side, this is also given, this is UDL. Because of this, that the slope will be WL by 24 EI, that is 50 into 6 cube divided by 24 EI. So this will be, this is 80 by EI plus this is 450 by EI. This is 530 by EI. That is the deflection along the coordinate 1 on account of the external loading. This is the simple calculation can initiate. Otherwise, you can adopt either conjugate method for this, and to take out separately, work out what is the slope here. This also you can take out separately, work out what is the slope here, and add the two, you get the same value. Next, along the coordinate 2, d2n is equal to, this is same as this, that is 450 by EI, already have worked out, and this is, I will use the third formula, that is 90 into AB. These distances, it is 2 meters and 1 meter, that is 2 into 1 divided by 6 EI into 3 into, this is left side slope I am calculating, so it is L plus B. B is 1, L is 3, 3 plus 1. So this value 3 plus 1. This is 4, 4 into 2, 8, 8 into 90, that is 720 divided by 18, 40. This is 450 plus 40, it is 490 by EI. I am getting positive sign only because same direction I have taken here as the coordinate. So therefore, your B, that displacement, it is nothing but dr minus dl. dl1, first one is 530 by EI. This next one, it is 0 minus 490 by EI, or this D matrix is 1 over EI minus 530 and minus 490. This is what to got. Displacement to find DL at all, that's what the DL. DL or D, I will say D itself. The displacement on account of the external load, that is second step. Then third step is to find the flexibility matrix. That is another important step. Third step, to find flexibility matrix. These are the only calculation steps. One is finding the displacement along the coordinates chosen on account of the external load. Next, development of flexibility matrix. No other calculation you have. This is all only from the standard tables. If you remember that for loading cases, you have to use. Suppose if combination of load is there, you superpose by taking one load at a time each and work out at the end. So I don't think you will get even triangular load or moment also will not be there. Even if it is there, that for those formulas also, you better remember, you can finish up the problem. Now first, since there are two coordinates, size of flexibility matrix will be 2 by 2. Size of F is 2 by 2. This you have to get first. That means your flexibility matrix elements will be 2 by 2 element, that is totally 4 elements, F11, F12, F21, F22. So these coefficients you have to evaluate by giving unit load and each of these coordinates one at a time. Now first we will just take the determinate B as usual. This is the determinate B. You give unit displacement along 1 first. That is, this is 1. I will give P is equal to 1 unit. Unit force. Unit force I have to give along each coordinate. Because when I give unit force here, it will displace in this fashion. Here also, it will displace in this fashion. And that other span will not displace at all. So this particular thing, we are calling it as F11. That is the displacement along 1 when load is given at 1 itself. And this is also F11. This is along the coordinate 2. That displacement is along coordinate 2. That is F2 when force is applied at 1. That is F21. So we have to work out. And this also, you know, whenever a beam is there, simply supported beam subjected to a moment at one end, then the displacement at that end will, the slope at that end will be L by EBI. And the slope at the other end is half of this value, that is of course ml by 3l, here it is ml by 6l. This already you have done even in your moment distribution method and all those things by explaining the carryover. This factor you have already seen or already used. That same thing I will use here also for calculating the flexibility coefficient. So here F11 for this span, L is 4 meters, it is 4 divided by 3EI. Next, for this it is 6 meters, it is span given, it is 6 by 3EI. So this is 10 by 3EI. That is your first element of this flexibility matrix. Then F21, that is also equal to F12, because always the property of flexibility matrix, it is a square matrix, square symmetric matrix. So that means it is, so all the elements are symmetric about the leading diagonal. Therefore F12 has to be F21. This is nothing but this 6 by 3EI. That is 2 by L by 6 here. So next you give unit the force along the coordinate 2 in this fashion, in the base indeterminate structure only. You give unit displacement. Because of this displacement in the structure will be like this. So this will be F12, this will be F22, this will be F22, this also F22. So therefore you can work out F12 is already have written here. It is 6 by 6 here.
Yes, sir.
Here also it is 6 by 6 here. Sorry. This I have taken 6 by 3 here. It is 6 by 6 here. Here because it is a T fast origin. ml by 6 here. So this will be 1 by EI. Here also it will be 6 by 6 EI. It is 1 by EI. Already I have written. Only F22 have to determine F22. Here it is 6 by 3L. Here it is 3L because unit load is applied at that end. So that is 6 by L by 3L. 6 by 3L. Here also it is 3 by 3L because that span is 3 meters. That's why 3 by 3L. So this will be 9 by 3L or it is 3 by L. Therefore, the flexibility matrix F is given by 1 over 3L. I will take it outside. 1 over 3L. Here F11 will be 10. F12 and this it will be 3 because 1 over 3L I have taken outside. This is 1 by L. Therefore, I have to multiply by 3. This also 3 and this will be 9. So this is my flexibility matrix. That is the simple calculation we have to do for evaluating the flexibility matrix. As you have done in stiffness, there you are giving unit displacement one at a time along each coordinate, keeping farther end fixed because force has to be generated. That's why you have to fix the farther end. Here, farther end you are not at all meddling. Yes, you are giving unit force along each coordinate and evaluating the displacement straight away. You are allowing the displacement. You are not constraining the farther end. There, you are constraining the farther end. That's all the difference between generation of flexibility and stiffness matrix. So you can find out F inverse also here itself. It's a 2 by 2 matrix. It is easy to find the inversion. So this 1 over 3i becomes 3i divided by this determinant of this particular thing is 90 minus 981. It is 81. Then adjoint of the transpose of adjoints. So this is nothing but 9. This is minus 3, 10. This is the inverse of the matrix which you can straight away write. Until degrees of freedom is 2 or 1 is a very simple process. 3 also you can do it with little bit extra time. Other than that, nothing. So these 2 steps are the major calculation steps. Then the last step, we have to evaluate the redundant. That is 4th step to find R. So in the first step I told, you have to evaluate dr and r. So dr already I have evaluated, dl also I have evaluated, d I have calculated straight away here. Then once I know d, f also I have found out, I can find the value of R. So for this we have to use the force displacement relationship. We know from force displacement relation D is equal to F into R P. Here I will use the value of R for the force. Therefore, this R is nothing but F inverse D. So all these I have evaluated in the previous 2 steps. In step 2, D I have evaluated. In step 3, I have evaluated F inverse. So I will strike this R is nothing but now, which is my MB MC. That is equal to F inverse 3A by 81, or this I can say EI by 27 into 9 minus 3 10 into D is, here I have evaluated 1 over EI into minus 530 minus 490. So EI get cancelled and 1 over 27, 9 into minus 530 minus 4,770, then this will be plus 3 into 490, 1470. And here it is minus 3 into 5, minus 530. Then here it is minus 4,900. This you can simplify. 1470 minus 4,770 divided by 27. How much you will get? 150.
300 divided by
27.
27. So we got minus 122.22.
122.22.
2.
Then what about this? 1590 minus 4,900 divided by 27.
By 27. Minus 122.59. 122.59.
This also. 122.56.
6.
So these are the moment. After dividing by 27. Okay, therefore MV is equal to minus 122.2 kilonewton meter and MC is minus 122.6 kilonewton. So you have found out the redundance. Now you can plot the bending moment diagram. So that is extra step. If it is asked, you can find out, otherwise here you can stop it. So now this is the beam given beam. I have found out the support moments. Here it is minus. So earlier I took here clockwise direction. Now I have to reverse this. This also I have to reverse. So these values is nothing but 122.2. Here on same lines, this also to be reversed. Instead of sagging, I am getting hogging movements and support naturally. So this will be 122.6 kilonewton meter. So these are the support moments. So now I will plot the bending moment diagram straight away. You take a horizontal line here. Here it is simply supported, 0 moment. Here I am getting tension. The tight side is here. I have to plot it there. 122.2. So join this and this. This is fixed moment diagram in AB. On this, I can superpose free moment diagram, which is 80 into 4 divided by 4. That is 80. It is like this. This is 80. This is 122.2. So this is the right moment diagram in the span AB. Here it is 122.6. It's a slightly more than this. So you can join this and this. So this is the free moment diagram for the span BC. On this you have to superpose free moment diagram. It is WL squared by 8. That is 50 into 6 square, 36, 50 into 36 divided by 80.
225.
8, it is 225. Like this. So here you will get 225. So this is the next bending moment diagram. So this is positive, negative, positive, negative. Then last is
0.
Pardon?
That is 0. T. M.
Next, of course, here it is 0. You can join. This is the fixed moment diagram. On this superpose free moment diagram, that is WAB divided by L.
60.
So that is 60. like this. This is 60, so this is negative, this is positive. This is the net bending moment diagram you are going to get. So with this much calculation, we have completed the entire process of analysis. In all the continuous beam, you follow these steps only. Always you select the redundant as the support moment. That is continuous joint support moment. Then indicate the coordinate direction as sagging. Then remember those standard cases formula, show the diagram and evaluate the DL matrix. Then DR matrix, if it is DR, normally it will be 0. If it is given, then you cannot select this as the redundant support moment. You have to select the vertical reaction. Otherwise, you can follow this as the general step. And once you calculate that D, that is displacement on account of the load, generate flexibility matrix by the usual procedure, then use the simple relationship, that is the force displacement relationship, D equals FR, and work out the redundant. The moment redundant is evaluated, you can plot the bending moment diagram. If shear force diagram is also asked, then you have to find the support reactions here. That means you treat each of these spans separately. You know the moment, you take the reaction, moment due to this reaction at one of the end support, evaluate that, then you can plot the shear force diagram. That I hope you already know. With this, all types of beam problems we have covered. Supplemental support and any other type of problem. I have already given in the beginning the type of problem you will get as per Silver. Because degree of static indeterminacy should not be more than 3. So as per that, this is the maximum you can get if it is simply supported, or one more span you may get it with all things. With fixed, number of spans get reduced automatically. Same case with the frame also. We will take up the frame problem in the next